So what we talked the last time is the procedure that you can do is the same uh, when you have only single chemical reaction, which is the way that you can determine the chemical reaction uh, coordinate through the equilibrium constant. So when you have more than one chemical reaction, the complexity will increase depend on how many reactions that you have, but the procedure is the same. The one is you will have the equation from the chemical reaction equilibrium. One is from the relation between the equilibrium constant and the fraction of the viscosity. And another one is the equation here for determining the equilibrium constant using the standard heat energy change and standard heat equation and also the heat capacity. And number of the equations that you have will increase depend on how many chemical reactions that you have. Okay. And when you have a system, you have a chemical reaction. You know the equation that you have. One thing that you have to consider before starting the calculation is you have to determine what the phase of the chemical species in the system exists. In the case that the chemical reaction consists of the gas phase species, in that case you can change or rearrange the equation a little bit based on the ideal gas phase. One thing is you can change the standard viscosity to the standard pressure, which is equal 1 bar. And another thing is you can change the viscosity in solution of species into the function of the mole fraction in gases and viscosity coefficient and also the total pressure here. And final, moreover, you can see that when you change the viscosity in solution into the function of the viscosity coefficient, it means that you have to further consider that in the case that you are considering, it can be assumed the viscosity coefficient can be unity or can be the viscosity coefficient of your species. For example, if you have a system that the chemical reaction carry out at a very low pressure and high pressure, higher than room temperature that we have, but the low pressure is the key. In that case, you can assume that all the gas species behave like the ideal gas. So in that case, you can assume that the viscosity coefficient in solution here equal unity, and in that case, you can get this form of equation. But if you cannot assume the ideal gas state because the chemical reaction is carried out at a very high pressure, in that case you have to determine the viscosity coefficient in solution, which is usually in the function of mole fraction in the white eye here, and it needs a procedure of iteration to calculation. All of this we have ever done it before in the previous examples and exercise. Okay, and this is the exercise 1 for the multi-reaction equilibrium. In this exercise, I just want to show you that what the procedure have changed when you have more than one reaction. So in this case, you have two reactions. So the thing that have changed is you have more than one values of the reaction coordinate. So in this case, you have two chemical reactions. You have two values of reaction coordinate, and you have two chemical reaction equilibrium as well. So when you have two reactions, you have two reaction coordinates. and also you have two equilibrium constants. So that's why you have two equations here. And in this example, we just do the same procedure that we have done before. One thing when you have the equation that has relation between the mole fraction and equilibrium constant already, you just change the form of the mole fraction into the reaction coordinate function. And you just rearrange the equation. And you can see that usually you will know the pressure that you carry out the chemical reaction. And if you know the temperature, you can determine the equilibrium constant for the reaction 1 and 2 as well. And so from the equation A and B here, only the unknown equation is the reaction coordinate for reaction 1 and reaction coordinate for reaction 2. So we have two equations, we have two unknowns, so usually in the principle you can solve it. And in this case, just eliminate the reaction coordinate for reaction number 2 by rewriting the equation A and B in terms of the reaction coordinate for reaction 1. And then you substitute back and solve for only one equation. Here is a purity step. So this is the second exercise for the multi-reaction equilibrium that we still use the method of the equilibrium constant to solve it. Today I will let you to use this spreadsheet to solve this exercise. But before that, you can see that before you can use the Excel or the software to solve this equation, you have many steps or many procedures that you have to done before to get the equation and put into the formula in the Excel. So in this exercise, you just have the known species that will exist in the system. You have the initial mole number of species in the system, and also you know the pressure, you know the temperature. And in this case, they want to find the mole fraction of each species at different temperature like this, and they provide you the standard heat energy of formation. So what we go through the last time is from this data, you can directly calculate the equilibrium constant by using the standard heat energy of formation here. Okay. Usually, what you know or what you have done so far in the previous exercises is you don't know the data or the value of standard heat energy chain formation at the specified temperature of the reaction. When you don't know the standard heat of formation at the specified temperature of the reaction, in this case you have to use the standard heat energy or the standard heat of reaction at the reference temperature instead for calculation of the equilibrium constant. Because in that case, you don't know this data at the specified temperature. So you have no way, no alternative, but using the data at the reference temperature to calculate the equilibrium constant. But if you can know the standard heat energy of formation at the specified different temperature, and in that case you can directly calculate the standard heat of energy using the standard heat of energy, standard heat of formation at that temperature. So in this case, it means that instead of using this long equation, you know the values or the data of the standard heat of formation at 1000, 1100, and other temperatures So then you can use this value to calculate the delta G dT directly. And this one is same with this parameter. So you can see that if you can calculate this parameter by using the stoichiometric number multiplied with standard deformation and summation for every species. Then you put back to in this equation by dividing by the gap constant and temperature here and take the exponential. You can know the equilibrium constants at that temperature. And before we can use the solver on the step or the Excel to solve this equation for you, you have to know the chemical reaction first. Why? Because you can see that this, for example, if you assume the ideal gas state, the equation that shows relation between mole fraction and equilibrium constant will be like this. So in order to solve this equation, it means that you have to clarify the ratio of the mole fraction here. And in order to do that, it means that you have to know what the chemical reaction occurs in the system. If you know what the chemical reaction occurs, then you can write the ratio of mole fraction here. But if you don't know, you just know the species in the system, for example, the ethylene, the ethane, the propylene, and you don't know the chemical reaction, then you cannot write this equation. So, in the exercise, the step that you have to start for using the equilibrium constant method to solve the multi-reaction equilibrium is you have to determine what the chemical reaction or how many chemical reactions occur in the system. So the procedure to do that is you have to starting by writing the formation reaction of the compound. So in this case, the compound that exists in the system is the water, carbon monoxide, and carbon dioxide. The carbon, hydrogen, and nitrogen is considered as the elements in this case, because the formation reaction for the carbon, hydrogen, or nitrogen gas is zero. There is no formation reaction. The nitrogen and hydrogen exist in the nature as two atoms bind together as a one molecule. But it's different from the compound. Compound, for example, is the consists of more than two elements in the chemical formula. For example, water is consists of the hydrogen and oxygen, and compound of the carbon monoxide is consists of carbon and oxygen elements. So in this case, you have to write the formation reactions for the water, carbon monoxide, and carbon dioxide. And after that, you have to consider that every formation reaction that you write still contain the elements that is not exist in the system or not. For example, in this case, carbon is also exist in the system, oxygen is also exist in the system. So it means that if there is no element, if every element that exists in the formation reaction that you write still exists in the system, it means that the total number of the chemical reaction that you write is already is a set of the independent reaction. So in this case, we have three chemical reactions for writing the equation of the equilibrium constant like this. So in this case, we just assume the ideal gas assumption, but if you go back to see pressure of the system, actually it is the 20 bar, and it's quite high, higher than the accuracy that you assume the ideal gas essentially. But for seeing the procedure how to use the equilibrium constant method to solve the problem, so just let's see that we assume the ideal gas solution, ideal gas state assumption. And the one more thing that we assume for solving this exercise is we assume that the pressure doesn't affect the viscosity of solid much because the solid is solid. Is you can say it's incompressible compound. You can say it's just like when you compare liquid and gas. In the case of liquid, the pressure has the effect on the liquid lower than the effect to gas. For example, if you have a piston that inside the piston that you have gas, when you push the lid of the piston by this means increasing the pressure, the volume of the gas will change very much. We can press the gas to change the volume, but if the piston that you have consists of the liquid water instead, you have to use much more of pressure to change the volume of the liquid inside the piston. This means that the pressure has the effect on the liquid lower than the gas. And it's same assumption to the solid as well. So the effect of pressure on the solid is very small because it changes the volume of the solid very little. So in this case, the pressure is related to the viscosity. So the ratio of viscosity of the carbon solid here we can assume at the unit. So if so, we can get the final three equations look like this. And from this equation, we want to clarify the mole fraction of each species. So we have to write the mole fraction of every species here, like this, to put back into the equation. And you can see, as I said, that in the case that we have to clarify what the mole fraction in the ratio in the equation look like this, you have to know the chemical reaction first. That's why we have to determine what the chemical reaction exists or will occur in the system. And now we know that there will be three chemical reactions. Then you can write the mole fraction of each species. So when you know the mole fraction, how function of the mole fraction in the term of the reaction coordinate already, then you put back into each equation of equilibrium constant. But in this case, to simplify the solution here, we just consider the value of the equilibrium constant for the reaction 1, 2, and 3, and we found that the equilibrium constant of the reaction 1, 2, and 3 here is very high. And if we look back to the equation, it means that if the left-hand side term is a very high value, it means that the denominator of the ratio here must be very, very small. So it makes the value on the left-hand side is a large number. So in this case, if this purple term here is very, very small, or if we can say that nearly zero here, what does it mean? It means that if you look back into the relation of the mole fraction for the oxygen here, which we have the purple term at the numerator here. So if purple term here is very small, nearly zero, it means that the mole fraction of oxygen must be very small as well, nearly zero as well. So it means that at the equilibrium, oxygen might not be exist anymore. So we have to look back into the chemical reaction system again. That we have to eliminate oxygen from the chemical reaction that we have written before, because from the consideration of the equilibrium constant and the mole fraction, we found that at the equilibrium, oxygen might not be exist anymore. So go back to the original three chemical reaction that we have written before. We want to eliminate oxygen from the reactions because as we consider so far from the chemical equilibrium constant. So in order to do that, you just do the mathematics of the chemical reaction together from three equations that we have. In this case, I just stick to the equation 2 multiplied with number 2 and minus with number 3. And with the operation by minus the equation reaction number 2 with the reaction number 1, you get the equation B here, reaction B here. So right now you can see that the reaction A and B that we have, we don't have the oxygen in the chemical reaction anymore. So, and every species that shown here in the reaction A and B is the species that exists in the system. So this is the new set of independent reactions in the system, and we have to starting over again to retain the mole fraction of each species to put back into the equation of the equilibrium constant and the mole fraction ratio and pressure here. So if you clarify the mole fraction of the new chemical reaction A and B already, you will get the equation A and B here. Okay. So you can see that if you know the temperature, you can calculate the equilibrium constant for reaction A and B, and you know the pressure. The standard state pressure is equal 1 bar, and you have the unknown parameter is the epsilon A and epsilon B. You have two equations, so it means that in principle you can solve the equation on it. You can use Excel or software function in the Excel to solve this one. Otherwise, you can do the iterative by yourself manually. It can be done as well. So, yeah, this is the example of how to determine the equilibrium constant for reaction A and B. This reaction A and B, and you can calculate the equilibrium constant directly using the standard gift energy chain formation of each species that exists in the chemical reaction. So if you look at the spreadsheet that I provided for you, so in order to solve this equation, this exercise, you can set up the table like this. We have a different temperature, but at the specified temperature, you can determine the equilibrium constants of A and B. And you have two equations. You have two equations, A and B here. So by guessing the initial value of the epsilon A and B and put the objective function for these two equations, you can solve for the epsilon A and B. And when you know the epsilon A and B, you can calculate for the mole fraction of every species by using this 1, 2, 3, 4, 5 relationship. Okay. And in final, this is the number of solutions that you should get in order when you use the following the preceding procedure that we talking about so far. The number might be changed a little from the decimal 3, yeah, 3 and 4, but it should be in this range. And if you plot the graph between the mole fraction of each species versus the temperature of the uh, chemical reaction, you can get the curve look like this. So, yeah. Um, so I will let you do first. Actually, I think the procedure from here is